Have you ever looked at the skyscraper or a complex machine or even just the phone in your hand and wondered, how in the world did they actually build that? Seriously, how did an idea in someone's head get translated so perfectly that thousands of people could create the exact same physical thing over and over again? Well, the answer is this hidden language that's all around us. And today, we're going to learn how to speak it.
Just think about it for a second. Try to describe only with words where every single steel beam, every electrical wire, and every window goes in a 100-story building. You just can't, right? You'd end up with a book bigger than the building itself, and honestly, it would still be a complete mess.
Exactly. You don't use words at all. You use a language that cuts right through all that confusion. It takes an abstract idea and turns it into crystal clear instructions. It's a visual language, and it's designed for one single purpose: to build. And that language is technical drawing.
Okay, so if we're going to call this a language, then what are the rules? What's its grammar? Let's start with a really clear definition of what we're talking about.
So at its core, it's all about visual communication. But this isn't just any communication. We're talking about conveying super precise, essential information for industry, for engineering, and leaving absolutely zero room for error.
And this is maybe the most important distinction we can make. In artistic drawing, it's meant to be interpreted. It's supposed to make you feel something. But a technical drawing, it can only have one single meaning. If two engineers look at the same blueprint and see two different things, that's a disaster waiting to happen.
And just like any living language, this one has changed over time. The tools that people use to speak it have gone through this massive, massive transformation.
For decades, drafting was this incredibly painstaking manual job. You had drawing boards, T-squares to get perfect parallel lines, triangles for just the right angles. A skilled drafter would spend hours, maybe even days, creating one single drawing. It took a ton of skill, a super steady hand, and a deep, deep understanding of geometry. Every single line you drew was a commitment.
And then, the first big revolution: 2D CAD. You can pretty much think of it as an electronic drawing board. All of a sudden, you could draw perfectly precise lines and circles right inside a computer. And its biggest strength? Making changes. A mistake that used to mean starting the entire drawing over could now be fixed with just a few clicks. It saved an unbelievable amount of time.
But the real absolute game changer was 3D CAD. This wasn't just about drawing lines on a screen anymore. No. With 3D CAD, you build a virtual part first, in 3 dimensions. The drawing is just a set of pictures of that digital object. And this is where the magic happens. You can digitally assemble all the parts, a whole car engine, an entire airplane, and see if they actually fit together before a single piece of metal ever gets cut. So it doesn't matter if you're using a pencil or a supercomputer, every single drafter faces the exact same fundamental challenge. How do you show a 3-dimensional world on a totally flat 2-dimensional surface? Let's get into the rules they came up with to solve that puzzle.
And this is it. This is the big one. This is the core problem that every convention, every rule in technical drawing is designed to solve. How do you take a real-world object that has height, width, and depth and show it accurately on a flat piece of paper or a screen?
The most common way to do it is with something called multi-view projection. Here's a way to think about it. Imagine you put an object inside a glass box. You look at it from the front and you trace what you see on the glass. Then you do the same from the top and then from the side. Now, if you unfold that glass box and lay it flat, you've got a perfect flat representation of the object from all the most important angles.
Okay, but what if the really important details are on the inside of the object? Well, that's where a section view comes in. It's a drawing that shows the object as if you took an imaginary saw and just sliced it right open. This lets you see all the internal shapes and features that would normally be totally hidden.
Oh, and if you've ever put together furniture from a flat-pack box, you're already an expert on this one. An exploded view drawing shows all the different parts of an object kind of separated from each other, like a controlled explosion. It's the perfect way to show how everything fits together and, crucially, in what order.
All right, so we've got the tools and we've got the grammar. Now let's talk about where this language is actually being spoken out there in the real world, every single day.
Well, one of the most obvious places is in how we design and build all of our buildings.
So here's a cool little detail. A floor plan isn't just a simple top-down view. It's actually a section view, like we just talked about. It's as if you slice the top of the building off about 3 feet above the floor.
And why 3 feet? Well, that's the perfect height to cut right through all the important stuff like doors and windows. Pretty clever, right?
And of course, technical drawing is the absolute lifeblood of pretty much every kind of engineering. This quote really says it all. In the world of manufacturing, a drawing is basically a contract. It's a set of instructions that has to be followed perfectly, sometimes to the thousandth of an inch. Accurately and unambiguously, that means there is zero guesswork allowed. The drawing tells the manufacturer everything they need to know to make the part.
So let's kind of wrap this up and think about the real power behind this whole visual language.
What makes this language truly universal? It comes down to standards. Things like ISO 128 create a global grammar for making things. It means an engineer in Japan can design a part, send the drawing to a manufacturer in Germany, and they can produce it perfectly without ever speaking a single word to each other. The drawing is all the communication they need.
And that kind of leads us to this final thought. You know, we've all heard the saying, a picture is worth 1,000 words. But a technical drawing, it isn't just a picture. It's a set of instructions. It's a plan. It's a precise, totally unambiguous piece of communication that lets us create nearly everything in our modern world. So what's the value of that? I don't know. It seems pretty immeasurable to me.